Let's use rotational Newton's laws and rotational energy to solve a problem that looks familiar, maybe hauntingly familiar. From earlier in the quarter, you should recognize this type of problem. Last time we saw this problem, the pulley was massless, so the tension on either side of the pulley and the rope was the same. And the pulley had no rotational energy because it was massless. Now the pulley has mass. We have the tools to deal with this. We can view our world a little more realistically. So a couple of questions that could pop up here. One question that we could ask about this problem is, what is the tension in the rope on either side of the pulley? Or what is the acceleration of the system? When you're asked for a force, like tension, or the acceleration, you should be thinking F equals ma. And when you're asked about speed and distance, like in part B, what is the speed of m2 just before it hits the ground, after it's dropped through a distance h, you should be thinking more in terms of energy conservation. I'm going to do this problem two ways. For part A, I'm going to use Newton's laws and solve it that way. For part B, I'm going to take a completely fresh approach and use energy to solve it. Of course, if I was doing these in order, I could use my acceleration from part A and some kinematics equations and figure out the answer to part B. But I'm going to do them sort of independently. So let's draw some free body diagrams. First thing I like to do. M1 and M2 are just moving linearly, like we've had objects moving in the past. And what do? We draw a dot to represent that object because they are not rotating. And let's see, M1 has a tension in the rope, kinetic friction force, a normal force, and the weight. Right? What's touching M1? The surface, which can interact through a normal force and a friction force. The rope, those are the only things that are touching it. And what can reach in from a distance? Gravity. M2 is hanging there. It has a tension pulling up on it. I'll call that T2. And the weight of gravity pulling down on it. Now you notice for the pulley, I didn't just draw a dot. I drew what we call an extended free body diagram. I drew a shape that represents the pulley, and I'm going to put the forces on there exactly where they act on the pulley. So where does tension 1 act? Right there. Tension 2 acts here. What else is acting on the pulley? Well, I have two more forces. Some kind of a support force is acting on it. The axle, right, is holding the pulley up, and the weight of the pulley is being pulled down by gravity. But those last two forces, the support force and gravity, those can't change the rotation of the pulley. They are just holding the pulley in place. Those can't make the pulley rotate if it's not rotating, and they can't affect the rotation at all. So we really don't care about them. They are not producing any torque. Their lever arms are zero. So now what do? We've got our free body diagrams, and we say the sum of the forces in the direction of motion is equal to m1a. The sum of the forces in the direction of motion is m2a, and the sum of the torque is I alpha. These are vector equations. I need to define my positive directions. I always like to pick the direction of my acceleration as positive. So my system is moving in this direction. That's the direction of the acceleration. So I'm going to choose that as my positive direction. So when M1 moves to the right, that's the positive direction. When M2 goes down, that's the positive direction. When the pulley turns clockwise, that's the positive direction. I need those all to be the same, or my accelerations won't be the same. So you can pick any direction you want to be positive for M1, but once you choose the positive direction for M1, that fixes the positive direction for the pulley and for M2. Otherwise, the accelerations won't be the same. So this is going to be to the right is positive, down is positive, clockwise is positive. Tension times the radius gives us the torque produced by that force, because we're looking for the lever arm. I'm going to draw it in red. The lever arm is the perpendicular distance. You extend the line of force and you look for that perpendicular distance to the axis of rotation, and that's the lever arm. In this case, it's just the radius of the pulley. Force times lever arm is the torque caused by T2. Force times lever arm is the torque caused by T1. And we add them up. Remember, T2 is causing positive torque. T1 is causing negative torque. We add them up and we get I alpha. What we're looking for is 3 equations and 3 unknowns. But we've got T1, T2, A, I, alpha. Let's work on I and alpha and try to get those into other variables that we can deal with. First thing we need to know is, what is this pulley? Oh, I didn't say, did I? Let's make the pulley a solid disk. I for a solid disk, 1/2 mr squared. What do we know about the tangential acceleration at the rim of the pulley? As this pulley is turning, the tangential acceleration, the acceleration of some point out here on the rim, is the same as the acceleration of the rope. And the rope's acceleration is the same as the acceleration as m2 and m1. So the tangential acceleration at the rim is equal to r alpha. The tangential acceleration is equal to r alpha, and at the rim it would be capital R times alpha. So that means that alpha is a over r. Now I can plug those in. The r's all cancel, and we've got our third equation. So 3 equations, 3 unknowns. T1, T2, and the acceleration. So let me go back up to this first equation. Friction force is mu times the normal force. Normal force is m1g. So I can plug this in for T1 down below. I can do the same thing here. And when I plug those in, what do I get? That's T2. That's T1. So I punched in the numbers. I got 3.51 meters per second squared for the acceleration. And we can go back and solve for T1 and T2 using these other equations. So I got 8.21 newtons for T1 and 12.6 newtons for T2. Now we'll attempt the same problem, but we're looking for the speed of m2 just before it hits the ground. We'll use energy. The initial mechanical energy, we would love it if it equaled the final mechanical energy, but there are a couple of things that get in the way. External forces and non-conservative forces like friction. So if we define our system big enough, we won't have any external forces. We'll include the Earth in our system. It's released from rest, so there's no kinetic energy initially. I'm going to call the floor my lowest point in the system. That's where M2 has 0 gravitational potential energy. So when it starts out, it's going to have gravitational potential energy. M1 never changes in height, so it doesn't have any gravitational potential energy change, so we don't have to account for it. And that's all the energy of the system initially. Nothing's moving. We're going to subtract the work done by friction, which is the friction force times the distance. And we're going to end up with things moving. M1 is moving. M2 is moving. The pulley is moving. But M2 is at its lowest spot now, so it doesn't have gravitational potential energy. There are no springs in this system, so I think that covers it. At the beginning, all the energy is in gravitational potential. At the end, it's all in kinetic, but we have a little less at the end because we lost a little bit of our mechanical energy to friction. M2GH minus the friction force times the distance, the kinetic energies, and for the rotational, 1/2 I omega squared. What is I for a solid disk? 1/2 mr squared. And we don't want omega in there. We really want all v's. So omega is v over r. Now we have everything in terms of V final. The R's cancel in the last term with the rotational kinetic energy term. So we can simplify this a little bit. And let's solve for V final. .59 meters per second. Just for fun, let's use the answer from part A in our kinematics equations to see if we can get the same final velocity. So M2 is falling. Let's define an origin, the floor. Let's define a positive direction, how about up? And let's fill in our chart like we would for any kinematics problem. It's going to start at some initial height, h. That was 3 meters in this case. It's going to end up at the floor. That's our origin, y equals 0. It starts from rest. V final, that's what we're trying to find. The acceleration we found in part A, it's 3.51 in the negative direction, downward direction. And time, we don't care. Let's find a kinematics equation that's missing time. How about this one? Fill in our quantities and solve for V final. .59 meters per second. The same thing we got using our energy equation. Whew! It all checks out. A quick review. When you see a problem like this, now the pulley has mass, the tension on either side of the pulley is going to be different, and the pulley is going to have some rotational energy. So if they're asking for a force, like a tension in the rope, or an acceleration, be thinking F equals ma, Newton's laws. I'm going to solve this using Newton's laws. Some of the forces equals ma, some of the torque equals I alpha. If they're asking for after some distance, what's the speed? Think energy. Use energy conservation.